So we're moving on with our circles unit. So this lesson is going to have to do with segment lengths and circles. But before we do that, let's do a little review here. So I want to ask you a couple questions. 1A, what term describes the point in the center of this circle ABC over here on the right? This circle is circumscribing the triangle, so it is the circumcenter. Our next question is what term describes DO, EO, and FO? So we're talking about DO here, EO here, and FO here. You should notice some right angles, which tells us it's perpendicular. You should notice tick marks here, which shows us that BA is being bisected by DO. So that's a perpendicular bisector. Third question is write a mathematical statement about AO, BO, and CO. So AO is here, BO is there, CO is there. You should see that all three of these segments go from the circle to the center. So these are all equal because they're all radii. Our next one down here has to do with this one. And once again, you should notice that this is a circle inscribed inside the circle, the triangle. So this is an incenter. What term now describes AP here, BP here, and CP here? And again, you should notice you got two, angle A is being bisected, angle B is being bisected there, and angle C is being bisected there. So these are angle bisectors. And once again, it's asking us about XP, YP, ZP. You should once again see that these are all radii of the circle, which means they are all congruent. All right, so the next one here, I would like you to pause the video, go through this, determine what each of these are, and then come back to me. So the radius is B, which is ZY, radius right there, ZY. The tangent is up here, that's RS, so that's F. The secant is TU down here, because it's a line that intersects the circle at 2 points. The tangent was a line that intersected the circle at 1 point. A chord ends, its endpoints are on the circle, so that was VW. Then we have a point of tangency, that's this point Q up here. Our center obviously is Z, and our diameter here is XY. So make sure you know all those terms and how to use them. So our vocab today is segments of chords, radius, diameter, perpendicular. These three terms right here we have used before. Segment of chords is new to us today. So our objectives are to solve problems with two chords that intersect a circle and solve problems with a radius or diameter and a chord that intersect inside the circle. So here's our theorem. First one, in a circle or congruent circles, two chords are congruent if and only if they are perpendicular. We know that they're perpendicular here by those right angle symbols in equidistance from the center of the circle. So that would mean that PM is congruent with PL. Those right angles between line BC and MP, that right angle there tells me those lines are perpendicular, and AD and PL are also perpendicular. That then means that chord BC is congruent with chord AD. So these chords out here are congruent because they're equidistant from the center and they are perpendicular from those lines that come from the center. The converse of this is also true. So if I tell you that CD is congruent with AB, then I know that they are perpendicular and that they are equidistant from the center. So the converse of this is also true. So now we're going to work through this problem. Example 1. If EO is equal to FO, so that means I can put some tick marks here on those, and AB is perpendicular to EO, that would mean a right angle symbol there, and CD is perpendicular to FO, put a right angle there, a right angle symbol. And then let's keep labeling. It says CD is 35 and AB is 6x minus 7. Now what we know, because they are equidistant, which is what those tick marks on EO and FO tell us, and right angles from there, we then can say that these two chords are congruent. So when we do that, we're going to set the two equations equal to each other. We're going to add the 7 to both sides, divide both sides by 6. So x is equal to 7 here. Now the way I can make sure this is right is I can plug that back up here into this equation. 6 times 7 is 42. 42 minus 7 is 35. And those two, A, B, and C, D, should both be 35. And if they're not, then I know I made an error somewhere. So this next one, again, we need to mark up what we see. KL is perpendicular to MN, so I got a right angle symbol here. PR and QN, another right angle symbol here. Then it says that KL this time, so this chord is congruent with PR. That means that they must be equidistant from the center. So that means I can say that MN is equal to QN. So that's what we're going to do when we set this up. Now let's go ahead and label these. So MN was 7x minus 8 and QN was 3x. What we're going to do once again is set these equal to each other to solve the problem. We're going to subtract 3x from both sides, and I added 8 to both sides. I'm going to divide both sides by 4, so my x is equal to 2. And remember, that's not asking me for x, so I have to plug this back in for MN, which means I'm going to do 7 times 2 minus 8, and that's going to be 14 minus 8, that's 6. Now the way, again, I can check this is by putting that 2 in there as well. 3 times 2 actually is 6, so again, that's a way to check the answer. So our next theorem we're going to go over today is if two chords intersect in the interior of a circle, then the product of the lengths of their segments of one chord is equal to the product of the lengths of the segments of the other chord. What does that mean? That means I'm multiplying parts, okay? So I've got this chord right here, AB, and I'm going to multiply AE times EB, and I'm going to set that equal to, here's my other chord, DE times EC. So what we're really doing here is we're multiplying part times part, and we're setting that equal to our part times our part. So right now we're going to work one of these. So let's go on to the next slide, the next problem. So this one says, example 2, SU is 5, so I'm going to go ahead and label SU as 5. It says that TU is 9, and then we have that VU is 15. It says that we're going to solve for RU. Well, I'm going to put an X up here because I just know most of y'all do better solving with X, but you could also do it with RU. It doesn't really matter. So when we do this one, again, we need to look at our chords here. So we have our whole chord here. So we're going to do TU times US, which would be 9 times 5. And then this other chord here, we're going to do the same thing with it. So we're going to break it up into its parts. So we're going to multiply RU, or X, times 15. So again, if you don't like the RU part, you can put X in there. So I'm doing RU times 15 is equal to 9 times 5. Obviously, 9 times 5 is 45. So that's 15 RU is equal to 45. We're going to divide both sides by the 15. So RU is going to equal 3 here. And the way, again, that we can check that is by putting that 3 up here. 3 times 15 is 45, and 9 times 5 is 45. Okay, so let's do the check it out. And again, remember you're multiplying part times part. So pause me, come back when you're done. Okay, so here again, we're multiplying 8 times 24, and we're setting that equal to 3x plus 1 times 12. That's how we're going to do this problem. So 8 times 24 is 192. Remember that we're going to distribute this 12 to each of these terms. Don't forget that. So when we do that, we're going to get 36x plus 12. After we do that, we're going to subtract, you know what, let me back up here a second so I can show you all this. So this is going to be 192 is equal to 36x plus 12. We're going to subtract the 12 from both sides. That's going to give us 180 over here. And then we're going to divide both sides by 36. So our x is equal to 5 here. So once again, we can double check this by doing 3 times 5 plus 1. That's 16. Multiplying our 16 times our 12, and that also equals 192. All right, so let's do this next one and label the parts. Again, come back to me when you're done. So this says CF is 10, BF is 8, then we have that EF is 2x, and DF is 2x plus 1. So here we go again. I'm going to multiply our parts times our parts. So we've got CF times FE is equal to BF times FD. That's how we're going to set it up. So we get 10 times 2x and 8 times 2x plus 1. So we get 20x over here and 16x plus 8 over here. Subtract the 16x from both sides. We get 4x equals 8. Divide both sides by 4. We get x is equal to 2. Once again, let's check this. But truth be told, we are looking for up here FD and FE. So let's go ahead and plug that x in. So when we do that, FD is equal to 2 times 2 plus 1, that's 5. FE is equal to 2 times 2, that's 4. So let's go ahead and plug these in now. This would be 4 here. So 4 times 10 is 40. And then this would be, what was it, 5 here. So then we got 5 times 8. That's also 40. All right, so this next one tells it basically is when we have a diameter or a radius that intersect a chord and they're perpendicular to each other, that means that the radius or diameter bisects that chord. So that would mean that from this point to E and from this point to F are congruent. Also, if we can see that they are perpendicular, then we know, they are being bisected, we can say that there's a right angle there. So let's go ahead and look at this next problem. So it says, how do we describe the relationship between the radius OB and the chord PQ? Well, OB is a perpendicular bisector of PQ. We know that because it is a radius. And we have a chord, and they intersect at a right angle. And then it says, what statement can be made about PA and QA? Well, PA and QA are congruent. So once again, we would have tick marks here. The next problem says, what can be said about XZ and YZ? So once again, we have a diameter this time that's intersecting a chord at a right angle, so we can say that XZ and YZ are congruent or equal. And the reason we can say that is because WD is a perpendicular bisector of XY. Then it asks us about, it tells us that DW, so this length right here is 10, and then it asks us about the length of DY. Well, if DW is 10, and it's a radius, DY is a radius, so it is also 10. So every radius in a circle is congruent. The next one says, what is the angle at point B? Well, I see that AB is congruent to AC, thus it's being bisected, and we have a radius, so that means there must be a right angle here. So that's a 90-degree angle, right? Because AB is congruent to BC and R's the radius is R is a perpendicular bisector of AC. And then it also asks us what two segments can be drawn that are congruent to DE. And y'all had E out here on yours. So this is where we're talking about DE here. That's a radius. So there are two other radii that can be drawn in this drawing. DC out here and DA right there. All three of those are the same length because they are all radii of the same circle. So now we're going to use this what we just went over for our next set of problems. So this is find NP. Well, to find NP, I'm pretty sure I'm going to have to find NS first. So to do that, what I'm going to do first is I'm going to draw another radius. I'm going to draw the radius RN. Then what we should notice is that Rn is equal to Rm because it's just another radius. And if you notice here, we've got the length of Rm, that's 17. Well, all radii are congruent, so I could say that Rn is 17. Now what you should see is that I have a right triangle. And hopefully you recall that I said the most frequently used theorem that we're going to use all year is Pythagorean's theorem. And so guess what we're going to use right now to solve for NS? We're going to use Pythagorean's theorem to solve for Sn. So we're going to plug in our values here. So 8 squared is 64, 17 squared is 289. We're going to subtract 64 from 289. That gives us 225. We will take the square root of both of these sides so that we can get just Sn. So Sn is 15. So we just found this length right here, it's 15. Well, we know because that's a radius and we have a chord that this length is the same as this length. So can't we do 15 times 2? Yes, we can. That's 15, y'all. My handwriting's getting pretty bad. So we just found that this was 15. And if that's 15, then obviously this down here has to be 15. So 15 times 2 is 30. That is the length of NP. Okay, so now go ahead and do this next problem and then come back to me when you're done. So finding QR, here again, we're finding the whole length QR. We're finding the length of the whole chord. So once again, we're going to draw another radius from P to Q. Notice again that we have PS, which is 20, which means that PQ is 20. So we can, once again, use Pythagorean's theorem to solve for our missing parts. So we're going to do TQ squared plus 10 squared equals 20 squared. That's going to be 100 from 400. That's 300. Take the square root of 300. That gives us 17.3. Then obviously, if we've got TQ up here at 17.3, then that means TR is 17.3. So we once again can multiply 2 times 17.3 to get 34.6.